Let us consider a small quantity of size of a slice of a pizza. So we are considering a pizza of a plane which is in 2D. I'm going to consider a small slice of a pizza. So one way of doing that is to specify the arc length of the outer edge of the slice and to form the slice by connecting the endpoints of the arc to the center. So one way of doing it is I'm going to connect this slice to the center here, and the more general specific, what we do is specify this angle here. Uh, Whatever the size of the pizza is, we are going to represent the quarter pizza no matter what the radius is. So for a circle of unit radius, the length of an arc is equivalent in magnitude to the plane angle and its subtends. Both are 2 pi for a complete circle of radius r is equal to 1. So to know this arc, whatever the length it is, the more specific is I find out the angle when it comes to a slicing of a pizza. On the similar background, now let us consider a watermelon. Now let us consider a watermelon which is in 3D, and let us attempt to quantify the size of the slice. Again, we can do it by specifying the outer surface area of the slice or by working with angles for generality. Connecting all the points at the edges of the slice to the center in case will form a three-dimensional body, and thus the angle at the center is this case is property called the solid angle. So I'm going to consider one small area here. What we do to cut this small area, I'm going to join it to the certain at the center of this watermelon with the perimeter of all the area which is connected to the center of that area. And to know that angle, it is again with the center, and that angle we call it as a solid angle, and that angle is been denoted by steradian. Now say for example, I'm going to consider one small area which I call it as A2. I have a small area here, and I call this as A2. I want to know the solid angle of this. So what I do is I join all the perimeter of this area to dA1. That is at the center of this area. Then what I do is with dA as a center, I draw a sphere of unit radius here. I draw a sphere of unit radius. Then the unit radius cuts this cone, which is the cone joining from A2 to dA1. It cuts at certain portion here, and that portion I call it as dA. Sorry, A. I call it as A, and the area of this A is nothing but it is equal to the solid angle. I repeat, I have certain portion of the area where in which we had considered a watermelon. On the similar background, I'm going to consider a small area A2. I'm joining the perimeter of this A2 to a small area dA1. With dA1 as a center, I'm going to draw a sphere of a unit radius. That sphere cuts this cone at a portion where that portion I call it as a area A, and that area A is equal to the solid angle. The same is written here below. Solid angle, construct a conical surface with vertex at dA1 passing through the perimeter of A2. A2 is this area. I'm going to construct a conical surface passing through the perimeter of A2. Then the solid angle subtended by the area A2 at the differential area dA2 is numerically equal to the area A of the portion of the surface of a sphere of unit radius at dA1, which is cut out by a conical surface. This is my conical surface, this is the area A, and my solid angle is equal to this area A. And in a 3D, solid angle is given by steradian and it is represented by SR. A hemispherical surface, and a differential area dA1 at its center. A hemispherical surface, I'm going to consider a hemispherical surface here. This is my hemispherical surface, and I'm going to consider a differential area dA at the center of this hemisphere. The solid angle subtended by this area, which is represented here, is equal to 2 pi, wherein which I can represent the solid angle for a hemisphere is equal to omega. It is represented by omega. So I'm going to integrate it with respect to d omega. So I have theta varying from 0 to pi by 2 and phi varying from 0 to 2 pi. So it will be sine theta d theta d phi. When I substitute, I'm going to get it as 2 pi. It is nothing but I'm drawing at the center of this dA1. I'm doing nothing but I'm drawing a sphere of unit radius. What I'm going to do, I'm drawing a sphere of unit radius here. When I draw a sphere of unit radius, so 2 pi r is nothing but my circumferential area. So r is nothing but it is equal to 1. So the solid angle subtended by area at dA1 is equal to 2 pi. So now I should know what is theta and what is phi. So the main thing, theta is nothing but for me, it is a zenith angle, and phi is nothing but azimuth angle. Phi for me, it will be varying along this surface. So this is my phi. The phi value, it is going to vary along this surface. So it is varying from 0 if I consider from this point. If I'm going to consider from this point, it is 0. Then I come back to here, it is 180. And again I'm coming back here. So minus 180 to 0. So the total is nothing but it is varying from 0 to 2 pi. So my phi is nothing but it is azimuth angle and it varies from 0 to 2 pi. I repeat, phi is nothing but azimuth angle and it varies from 0 to 2 pi. And I have a zenith angle that is nothing but theta, and theta is going to vary for me only from 0 to pi by 2, that is from 0 to 90 degrees. It is going to vary, theta is going to vary from 0 to pi by 2, and uh, phi is going to vary from 0 to 2 pi. That is from this end to pi, and from again minus 180 to 0, so it will be 2 pi. So I repeat, phi is nothing but azimuth angle. It varies from 0 to 2 pi, and theta is nothing but zenith angle. It is going to vary from 0 to pi by 2. So I'm going to consider a small portion which is given here in pink in color. So the same thing I'm going to consider here. So I have a portion of a hemisphere where I'm going to consider dA here. This part I'm going to consider it as a dA, or this is my small area which I'm going to consider. So to know the solid angle, what we have done, we have joined the perimeter of this area to the midpoint of this surface. This arc length in this portion, this arc length is given by r sine theta d phi, and this arc length is given by r d theta. So the area of this will be nothing but r sine theta d phi into r d theta. So I'm going to get it as r square sine theta d theta and d phi. So the area of this surface at the surface, I'm going to get it as r square sine theta d phi d theta. So that is the area for me given subtended at the small area dA1. So we are going to find out the solid angle, and solid angle is given by omega. I know what is the solid angle which we have. Now say for example, so this part is nothing but for me it is theta. Then when I consider the variation of this, when I consider the variation of this, for me this is nothing but d phi. This angle what I get, this angle what I get is nothing but d phi. I'm going to find out the area at this portion. So this is nothing but dA. I'm going to find out dA. The length of this arc, the length of this arc, it is nothing but r d theta, and the length of this arc, it is given by nothing but r sine theta d phi. So area is nothing but this multiplied by this. So dA will be nothing but, it is nothing but r d theta multiplied by r sine theta d phi. So this is nothing but for me r square sine theta d theta d phi. So dA is nothing but r square sine theta d theta d phi. So the solid angle d omega, it will be is equal to the area divided by the square of the distance. So dA by r square. So dA is nothing but r square sine theta d theta d phi divided by r square. So this will be nothing but sine d theta d phi. So this is in the spherical coordinate system. Now this is for me nothing but the solid angle. Now I'm going to find out the total intensity of radiation. Total intensity of radiation. It is nothing but the radiant flux, passing in a specified direction, per unit solid angle. Total intensity of radiation is nothing but radiant flux passing in a specified direction per unit solid angle. Say for example, I have a surface, and this surface, let me consider a small area of this surface. It is emitting rays in all the directions. Let me consider only one ray which is going in this direction. I'm going to have a small cone. I'm going to have a small cone in this direction. If I consider the rate of emission going in this cone, it is nothing but, I call it as dE, because I'm going to consider a small radiant flux going through this cone, and it is with respect to the solid angle. I call it as d omega. It is with respect to a small angle, and that small angle I call it as d omega. So the intensity of radiation is nothing but the radiant flux passing in a specified direction, per unit solid angle. So intensity of radiation is nothing but the radiant flux passing in a specified direction per unit solid angle. So I is equal to dE by d omega. So dE in our case is equal to nothing but I into d omega. So if I want to know the radiant flux, I'm going to integrate it on both the sides. So it will be nothing but E is equal to integration of I into d omega. And when the integration what I have here, when this integration is carried out for the whole hemisphere. When this integration is carried out for the whole hemisphere, what happens to this integration? What happens to this integration? It is E is equal to, I am going to have zenith angle as well as azimuth angle. So my zenith angle, it varies from 0 to pi by 2, and azimuth angle varies from 0 to 2 pi. So I have, it is 0 to 2 pi, and this is varying from 0 to pi by 2. So I have, it is I into d omega, and I know d omega is nothing but d omega from this equation is nothing but sine theta d theta d phi. From this equation, d omega is sine theta d theta d phi. So I substitute the value of d omega in this equation. It is 0 to 2 pi, and this is 0 to pi by 2. It is sine theta d theta d phi. Sine theta d theta d phi. And for many cases, say for example, I have a surface here, and I have a small area from this surface where I have a radiation going in one direction, and I call the intensity of this radiation as I, and I have a normal to this direction of this intensity of radiation which is going out. I take it as IN, intensity of radiation in the normal direction. This is nothing but I'm going to consider it as a normal direction, for which we are going to have the value of theta. According to our Lambert's law, according to the Lambert's law, here we come across one more law, and we call it as Lambert's law. According to the Lambert's law, I have intensity of radiation I is equal to In cos theta. In cos theta. So intensity of radiation is in the normal direction is In cos theta. So I substitute this back in the equation. So it is E equal to 0 to 2 pi into 0 to pi by 2. I have In sine theta cos theta d theta d phi. D theta d phi. So I integrate this equation. It will be nothing but I have In. The first integration is d phi, that is phi. Phi varies from 0 to 2 pi. I have the second integration 0 to pi by 2. It is sine theta cos theta d theta. This In I'm taking it is a constant, so I'm taking it outside the integration. So within the integration, I have integrated only with respect to d phi. D phi integration is nothing but phi, and it is varying from 0 to pi by 2. When I substitute the limits, I get In into 2 pi. Then I have an integration with respect to 0 to pi by 2. Then sine theta cos theta d theta. Here what I do is I multiply and divide by 2 in the numerator and the denominator. So this portion within the bracket, it is 2 pi into In. This is 0 to pi by 2. It is sine 2 theta divided by 2 into d theta. So this is nothing but 2 pi in divided by 2. 2 I am taking it outside. The integration of sine 2 theta will be nothing but cos 2 theta divided by 2. And the limits are 0 to pi by 2. So when I substitute the limits, I will be getting as 2 pi in by 2. Here I have nothing but minus cos pi plus cos 0. So this will be nothing but I have pi into in. This is divided by 2, I guess. It is again divided by 2. So this is nothing but I get minus of minus 1 plus 1 divided by 2. So this is nothing but pi into in. So this is 2 divided by 2. It gets cancelled. I am going to get pi into in. So E is equal to nothing but pi into in. So for any surface, it is diffuse. So I have a emissive power of a body is pi times the intensity of radiation. Emissive power of a body is pi times the intensity of radiation. Wherein which when I see most of the question papers where I have proved that the emissive power of a body is pi times the intensity of radiation. So this derivation, most of the previous year question papers, they have asked. That is proof that emissive power of a body is pi times the intensity of radiation. So I'm going to start this derivation from the solid angle, then intensity of radiation, then the Lambert's law, and then integrate, substitute the limits, come to the conclusion that is emissive power is equal to pi times the intensity of radiation. To do this derivation, we come across a law which is nothing but Lambert's law. Lambert's law states that intensity in intensity of radiation going in a direction, normal direction, multiplied by cos of that theta is equal to the intensity of radiation. So I is equal to in cos theta gives me the Lambert's law, and also the total intensity of radiation, it is the radiant flux passing in a specified direction per unit solid angle. So I'm going to talk this in the radiant flux which is going in a solid angle. So it is taken by I is equal to dE d omega. So this is all about today what we are going to take it. It is the emissive power of a body is pi times the intensity of radiation. Anybody have any doubts? If you have any doubts, you can clarify. Anybody have any doubts? You can just